Outside the space station, the vacuum will take you in seconds. A hole the width of your hand is enough. That's as dangerous as it ever gets. Out at the moon, it's the same vacuum. At Jupiter, the same. 10 billion kilometers out, past everything we've mapped. Still exactly the same vacuum. Space doesn't get more hostile the further you go. It's identical the whole way out. So why does every kilometer make it worse? Why is a person at Mars in more trouble than a person in orbit when nothing around them has changed? Because something is being taken at every step. And by the end of this video, you'll know exactly what, one step at a time, all the way to the last one. Now get yourself comfortable, hit subscribe, we begin. 420 kilometers above your head, about 260 miles, there is a pressurized metal cylinder with people inside it. That distance is smaller than it sounds. If you could turn your car upward and drive straight into the sky at ordinary highway speed, you would arrive in under 4 hours, less time than a long day at work. The International Space Station is not far away. It is directly overhead, and it is closer to you than many capital cities are to each other. Inside that cylinder, the air is kept at the same pressure as the room you are sitting in. The temperature is held around 22 degrees Celsius, about 72 Fahrenheit, the setting most offices use. People float through it in t-shirts. They eat, argue, sleep, and take photographs of the planet turning underneath them. And they orbit that planet once every 92 minutes. Let's start with what that number actually does to a human day. 92 minutes per orbit means 16 sunrises and 16 sunsets in every 24 hours. Standing where you are now, watching 16 dawns would take you 16 days. More than 2 weeks of your life, 2 weeks of alarms, of coffee, of weather changing. Up there, that entire fortnight of sunrises is compressed into a single working shift. The sun comes up, floods the cupola windows with light, and drops below the curve of the Earth again before the crew has finished a task. Your body has no equipment for that. Every internal rhythm you own was calibrated by a planet that turns once a day, and the station breaks that calibration 16 times before bedtime. Now consider what waits on the other side of the aluminium. Outside that hull, the pressure is functionally zero. Not thin air, not high-altitude air. True vacuum. If the hull opened, a breach the width of your hand, the cabin atmosphere would begin leaving faster than anyone could stop it. Here is the part that matters, and it comes from decades of NASA and US Air Force decompression research, some of it grim, most of it done on animals, a few cases documented on humans by accident. A person in full vacuum keeps useful consciousness for somewhere between 9 and 15 seconds. That is the entire window. Not enough time to reach a hatch at the far end of a module. Barely enough to reach one that is already beside you. In 1966, a technician at NASA's Johnson Space Center had a suit fail inside a vacuum chamber. He lost consciousness in about 14 seconds. When he woke, he said his last memory was the saliva on his tongue beginning to boil. That is what sits 9 millimeters from a sleeping astronaut's shoulder. So when astronauts on the station look into a camera and say this is space, they are telling you the exact truth. The vacuum is real. The danger is real. Nothing about that is exaggerated. And yet, they are also, in a way almost nobody thinks about, still inside the Earth. Not on it. Inside it. Inside its systems, its protections, its reach, its weather. Low Earth orbit is not the beginning of the void. Low Earth orbit is the last address that still receives deliveries. Picture Earth as a house, not a planet. A house with rooms and floors and a staircase. The station is the highest room in that house. The window is terrifying. The drop is real. But the plumbing still reaches it. The wiring still reaches it. Somebody still climbs the stairs with a box of oranges. Everything that follows in this story is about what happens when you step outside that house, and how many things you are leaning on without ever once noticing them. Let's talk about the first one, because it is the one people get wrong most often. The atmosphere does not stop at the station. At 400 kilometers, the air density is roughly half a trillionth of what it is at sea level, a number so small it barely deserves the word air. And still, it drags. Think of walking through waist-deep water. Now think of the same resistance, reduced almost to nothing, but applied to a 450-ton structure moving at 7.5 kilometers per second, about 17,000 miles per hour. Even a whisper of gas, hit at that speed, becomes a brake. The station loses roughly 100 meters of altitude every single day. About 2 kilometers, a little over a mile, every month. Left alone, it would spiral down and burn. So a few times a year, a docked spacecraft fires its thrusters and pushes the whole station higher. They call it a reboost. Strip away the terminology, and here is what it means. Earth is still physically pulling on those people, and they have to keep pushing back forever, or they fall home. And this is where two facts sit awkwardly beside each other. Astronauts float, so most of us assume gravity has released them. But gravity at that altitude is still about 90% as strong as it is under your feet right now. They are not weightless because gravity let go. They are weightless because they are falling permanently, and the planet keeps curving away underneath them at exactly the rate they fall. Every one of those people is in an endless, controlled drop. The house has not released them, not even slightly. Beneath everything, beneath the oceans, beneath the crust, beneath the mantle, Earth's outer core churns as molten iron. That moving metal generates an electric current, and that current generates a magnetic field that reaches far out into space. Scientists call it the magnetosphere. What it actually is a shelter, and it is not a sphere at all. The solar wind, a constant stream of charged particles blowing off the sun, slams into it and squashes it. On the daylight side, the field is crushed inward to roughly 10 Earth radii, about 65,000 kilometers, or 40,000 miles. On the night side, the same wind drags it out into an enormous tail that stretches hundreds of Earth radii, far past the Moon's orbit. Imagine a candle flame in a steady breeze, blunt and compressed on the windward side, drawn into a long streaming point behind. That is the shape of the thing protecting every human being who has ever lived. You have already seen it working. Auroras are what it looks like when charged particles get captured and funneled down the field lines toward the poles. Those green and red curtains over Norway and Alaska are not decoration. They are a receipt, visible proof that something was caught before it reached you. The station flies deep inside that shelter, below the trapped radiation belts, below the worst of it. Crews still take a dose, roughly 80 to 160 millisieverts over a 6-month stay, according to NASA's own figures, varying with the solar cycle. Here is what that means in a life. On the ground, natural background radiation gives you around 2 to 3 millisieverts a year. So, a 6-month expedition delivers something like 30 to 60 years of ordinary Earth exposure, an entire lifetime's worth, absorbed between spring and autumn. That is the protected number. Remember it. The second connection is one you use every day without noticing. Above the station sits a ring of NASA relay satellites in geosynchronous orbit, the Tracking and Data Relay Satellite System. The station's signal goes up to one of those relays, down to White Sands in New Mexico, and across to Houston. Round trip, under a second. Before that network existed, spacecraft in low orbit could talk to the ground for only about 15% of each orbit. Now, it is over 95%, nearly always connected, and what that buys is not data, it is presence. An astronaut reads a bedtime story to a child who is actually listening, in that moment, and answers back. A married couple has an argument in real time, with real pauses, the way arguments are meant to happen. A school class asks a question and gets the answer while the hands are still up. Mission Control does not monitor the station. Mission Control rides along with it. Specialists in Houston watch individual subsystems so closely that they often see an anomaly, a pressure drift, a pump behaving oddly, before anyone aboard notices anything at all. Think about what that actually means. Someone on the ground is watching your life support more carefully than you are, and they can tell you, right now, in this second, there is always a way out. At every moment, a Soyuz or a Dragon capsule sits docked to the station, not to carry cargo, not for research. It is there as a lifeboat, and for no other reason. On December 14th, 2022, that arrangement was tested. Cameras caught something spraying from a docked Soyuz MS-22, a stream of frozen flakes venting into space. The coolant loop had been holed, most likely by a micrometeoroid, and the vehicle emptied itself. 3 people, cosmonauts Sergei Prokopyev and Dmitry Petelin, and NASA's Frank Rubio, suddenly had a ride home that engineers no longer trusted for a normal return. The response tells you everything about where the station sits. Roscosmos built a fix and flew it. On February 23, 2023, Soyuz MS-23 launched with no crew aboard, just a small teddy bear tethered inside as a zero-gravity indicator and docked to the station as a replacement lifeboat. That is the deepest truth about low Earth orbit. When your escape route breaks, a new one can be manufactured on the ground and delivered to your door in weeks. And if the decision ever comes to leave immediately, the timeline is this. From undocking to a capsule on the ground in Kazakhstan with recovery helicopters inbound is about 3.5 hours. Shorter than a domestic flight. Shorter than some people's commute across a bad city. Hold that number. 3.5 hours. It becomes important later, in a way you will not like. The last connection is the humblest and the easiest to overlook. Cargo ships arrive every few weeks. Food, spare parts, filters, experiments, letters, and fresh fruit, which sounds trivial until you understand that after 2 months of packaged meals, the smell of an orange opening in a sealed metal room is something crews describe for years afterward. If something critical fails up there, engineers on the ground can design it, machine it, test it, and fly it. Not in principle, in practice, within weeks. Nothing aboard that station is truly irreplaceable because the factory is still reachable. None of this makes low Earth orbit safe. It is genuinely lethal, and pretending otherwise would insult the people who live there. NASA's Orbital Debris Program Office counted 35 occasions between 1999 and 2023 when the station had to fire engines and move out of the path of tracked debris. On a handful of other occasions, the warning came too late to maneuver at all, and the crew simply retreated into their capsule and waited to find out. The hull outside swings from about 121 degrees Celsius in direct sunlight, 250 Fahrenheit, hot enough to boil water twice over, down to minus 157 or minus 250 Fahrenheit in Earth's shadow. That full swing happens every 92 minutes. 16 times a day, the station's skin travels between an oven and a deep freeze. And yet, since November 2nd, 2000, when Bill Shepard, Yuri Gidzenko, and Sergei Krikalev floated aboard, there has not been a single day when no human being was living in space. More than 25 unbroken years. No crew has ever died aboard that station. Anyone born after that date has never experienced a day on which every living human was on the planet. That record is not luck. It is 4 connections, a magnetic field, a voice with no delay, a door, and a delivery route, working simultaneously every second for a quarter of a century, which creates a problem nobody has solved. Everything we know about humans living in space for long periods, we learned in a place where help was always 3.5 hours away, where a familiar voice answered instantly, where the oranges kept coming, and researchers disagree sharply about whether that knowledge transfers at all. One position, argued in a European Space Agency review of analog research and echoed inside NASA's own human research program, is that the station is a poor model for deep space precisely because it is so well connected. Near real-time communication, evacuation capability, resupply, and magnetic shielding are all present. The single psychological condition that defines a deep space voyage, what the literature calls the Earth out of view phenomenon, the experience of not being able to find your home planet in the window, has never been produced there, or anywhere, by anyone. The other position holds that the station can be modified into a meaningful analogue, impose artificial communication delays, force medical autonomy, restrict resupply, and study what breaks. NASA has published concrete plans to do exactly that. Both sides are working from real data. Neither has the measurement that would settle it, because that measurement has never been taken by a human being. There is a reason the psychology aboard the station does not carry a particular kind of dread. Crews get bored, they get irritated, they miss their families badly, but they are not beyond help, and some part of the animal in them knows it. That baseline has an expiry date. NASA plans to retire the station around 2030, and SpaceX is building a purpose-made vehicle to push 430 tons of it down into the remote South Pacific. When it goes, humanity loses its only long-duration safety net, the one place where we have ever proven people can live off Earth for years without dying. But that is not the strangest thing about that high room in the house. The strangest thing is this: every protection described here, the magnetic shelter, the instant voice, the lifeboat, the delivery route, all of it stops at a boundary, a specific altitude, an invisible line drawn in the sky above the station, made not of metal but of radiation, discovered by accident in 1958 by an instrument that everyone initially assumed had failed. Not one person living on the International Space Station has ever crossed it, and on the other side, the house ends. The house ends at a fence nobody built. You cannot see it. No instrument on the station registers crossing it, because the station never does. But every human being who has ever left low Earth orbit has passed through it, and every human being who ever will must pass through it too. We found it by accident, and at first we thought our equipment had broken. On January 31st, 1958, a Juno rocket lifted a slender cylinder off a pad at Cape Canaveral. Explorer 1, America's first satellite, 13.5 kilograms, about 30 pounds, roughly the weight of a large bag of dog food. Bolted inside was an instrument designed by James Van Allen of the University of Iowa, a Geiger-Miller tube. If you have ever seen a film where someone waves a clicking wand over contaminated ground, you already know the device. Every time a charged particle passes through the tube, it produces a pulse. More particles, more clicks. The data came back and made no sense. At lower altitudes, the counter behaved beautifully, around 30 counts per second, close to what cosmic ray theory predicted. Then, on passes above roughly 2,000 kilometers, about 1,250 miles, the counter reported nothing at all. Zero. Van Allen and his graduate student George Ludwig had a problem every scientist dreads. Either the universe was empty in a place it had no business being empty, or their instrument had failed. It had done neither. Carl McIlwain, another member of the Iowa group who had personally calibrated the detectors, recognized what everyone had temporarily forgotten. Push enough radiation through a Geiger tube and the pulses stop being separate pulses. They smear into one continuous signal, and the circuit reads that as nothing. A later laboratory test confirmed it. At more than 35,000 counts per second, an identical sensor reported a flat, clean zero. Think of a microphone held in front of a jet engine. The tape does not record a roar. The tape records silence because the sound has exceeded what the equipment can express. That silence was the discovery. The counter had not gone quiet because nothing was there. The counter had gone quiet because too much was there. What Van Allen's team had found, confirmed weeks later when Explorer 3 flew with a tape recorder aboard and returned data from a whole orbit, were two enormous rings of trapped particles wrapped around the planet like a pair of invisible tires. Charged particles cannot cross magnetic field lines easily. They spiral around them. So particles caught in Earth's field become prisoners, bouncing back and forth between the poles, thousands of times a second, sometimes for years. The inner ring begins around 1,000 kilometers up and reaches out to about 6,000, roughly 600 to 3,700 miles. It is dominated by protons moving at tremendous energy. The outer ring sits far higher, from around 13,000 kilometers out to 60,000, about 8,000 to 37,000 miles, and it is mostly electrons. Between them lies a relatively calm gap that physicists simply call the slot. Both rings breathe. They swell and shrink with solar activity, and their exact boundaries change depending on which measurement you trust and which day you take it. What matters is the shape. 2 loaded rings, 1 quiet lane between them, and beyond it all, the field thinning out until it can no longer hold anything at all. And here is the detail that reframes everything you have been told about the space station. The station orbits below the inner belt, permanently, deliberately. Those crews are not living beside the radiation belts. They are living underneath them, sheltered by the same trapped particle structure that would irradiate them if they climbed into it. The belts are not a hazard the station survives. The belts are the ceiling of the room the station lives in, which raises the obvious question, and it is worth asking plainly, why not simply fly around them? You cannot, not usefully. The belts wrap the planet, and every efficient path outward, every trajectory that does not waste enormous quantities of propellant climbing over the poles, punches straight through. Getting anywhere means going through the fence, not around it, through it. Apollo proved this could be survived. Those crews crossed the belts quickly, along paths threaded through their thinner regions. NASA's own teaching materials put the transit through the most intense zones at well under an hour. Dosimeters carried by the Apollo astronauts recorded no more than about 2 rads for the entire journey out and back, a smaller total than a modern crew absorbs on a 6-month rotation aboard the station. No acute effects were ever detected, so the belts do not kill you. But that was never the real point. Here is what most people misunderstand about the Van Allen belts. They are not primarily a wall of danger. They are a boundary of jurisdiction. Below them, Earth is doing the work. The field, the atmosphere, the relay satellites, the lifeboat, the delivery route. Above them, the planet's authority thins, and the responsibility transfers to the vehicle. Crossing the belts is not the hazard. Crossing the belts is the moment the paperwork changes hands. For 53 years, no human being made that crossing. Then, on April 1st, 2026, 4 people did. The flight almost did not happen when it was supposed to. Through February, the Space Launch System rocket sat on Pad 39B at Kennedy Space Center and refused to cooperate. A wet dress rehearsal on February 2nd, a full practice countdown with the tanks loaded, ended early because of a hydrogen leak at the base of the rocket. The February window closed. Engineers pushed to March. Then, on February 21st, technicians observed an interrupted flow of helium through the upper stage. The whole stack rolled back 4 miles to the Vehicle Assembly Building on February 25th. It returned to the pad in the 3rd week of March. At 6:35 in the evening, Eastern Time, on April 1st, the engines lit. 8.8 million pounds of thrust. The number means nothing until you set it against the vehicle itself. The fully fueled stack weighs about 5.75 million pounds, so those engines were producing half again more force than the entire rocket weighed, which is why it did not simply sit there and burn. More than 3/4 of that force came from the 2 solid rocket boosters strapped to the sides, about 17% more thrust than the Saturn V that carried Apollo. Inside the Orion capsule, a spacecraft the crew had named Integrity, sat Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen. 2 minutes up, the boosters burned out and fell away. 6 minutes later, the core stage followed. The upper stage lit and placed Orion into a stretched egg-shaped orbit around Earth, a low point of about 115 miles, a high point out near 44,500. And then, for about a day, they simply stayed there. That day in high Earth orbit was the safest part of the flight, and everyone involved knew it. The crew ran a proximity operations demonstration, flying Orion manually around the discarded upper stage, closing to roughly 10 meters, about 30 feet, using hand controllers, checking how the vehicle actually handles when a human being is steering it. They tested systems, they looked out of the windows. They were, in every meaningful sense, still home. Then, on the evening of April 2nd, they strapped in. At 7:49 Eastern Time, the engine on Orion's European-built service module fired for 5 minutes and 50 seconds. That burn is called trans-lunar injection, and it deserves to be understood properly, because it is the single most consequential thing that happens on a lunar flight. An orbit is a closed loop. You fall, the planet curves away, you keep falling, forever. Trans-lunar injection adds enough speed to break the loop open. The circle becomes a long, stretched arc, and the far end of that arc no longer comes back around. Picture a stone whirled on a string, and the string being cut. After that burn, Orion was not orbiting Earth anymore. It was falling away from it. Laurie Glaze of NASA marked the moment plainly. For the first time since Apollo 17 in 1972, humans had departed Earth orbit. We knew roughly what those 4 people were flying into, because a machine had already done it. In late 2022, Artemis 1 flew the same corridor with no one aboard, a 25-and-a-half-day mission carrying 5,600 passive radiation sensors and 34 active detectors, plus 2 life-sized measuring mannequins named Helga and Zohar, built with dosimeters seeded through their torsos, where a human being's organs would be. A collaboration between NASA's Space Radiation Analysis Group, the German Aerospace Center, and the European Space Agency. The results appeared in Nature in 2024, and one finding should change how you picture a spacecraft. Radiation exposure inside that single capsule was not uniform. During the passage through the inner proton belt, detectors in the least shielded positions recorded peak dose rates up to 4 times higher than detectors sitting in the vehicle's most protected corner. 4 times. Inside one small vehicle. Depending on where you were sitting, imagine 4 people in a room the size of a large car. Sit in one corner, and the exposure is 1 figure. Sit in the opposite corner, and it is quadruple. Nothing about the room looks different. Nothing feels different. No one inside would ever know. Then came the second finding, and this one was closer to a gift. Partway through the proton belt, Orion rotated. A routine attitude change, made for entirely unrelated reasons. The dose rates inside dropped by roughly half. The particles trapped in that belt do not arrive from everywhere. They spiral tightly around magnetic field lines, forming something closer to a plane of radiation than a fog. When the vehicle turned, it put its heavy structure, tanks, equipment, dense hardware, between that plane and the interior. An umbrella held at the wrong angle keeps you no drier than no umbrella at all. Turn it into the rain, and you stay dry. That is the whole mechanism, half the dose, from a turn. And this is the philosophical shift buried inside all that data. Below the belts, radiation is Earth's problem, and Earth solves it with a molten iron core and a field that reaches 65,000 kilometers toward the Sun. Above the belts, radiation becomes the spacecraft's problem, and the spacecraft solves it with mass, geometry, orientation, timing, and a quantity nobody likes to name out loud: luck. Orion is designed so that a large solar particle event delivers, at most, about 150 millisieverts to a crew sheltering in the most protected part of the vehicle. To put that beside something familiar, a 6-month stay on the station typically runs 80 to 160 millisieverts over half a year. Orion's design limit absorbs a comparable amount in the span of a single storm. The Nature team also found something reassuring. Galactic cosmic ray dose rates inside Orion ran as much as 60% lower than earlier spacecraft measurements had suggested. The shielding works better than expected. But here is the problem. No solar particle event occurred during Artemis 1, none during Artemis 2 either. So that 150 millisievert ceiling, the number the entire storm shelter design rests on, has never been tested against a real solar storm with a real vehicle in real deep space. The 4-fold figure quoted for a reference event, the Great October 1989 storm, comes from simulation. Good simulation, carefully validated against belt data, simulation nonetheless. Suppose the sun had let go during those 10 days in April. We believe we know what would have happened. We have never watched it happen, and the belts themselves remain less predictable than most people assume. For decades, engineers built spacecraft using the AE-8 and AP-8 trapped radiation models dating from the 1980s. Their successors, AE-9 and AP-9, were designed specifically because the old models' limitations were well known, and the newer ones carry explicit uncertainty bands rather than single confident numbers, precisely because the honest answer includes a range. Then the Van Allen probes went up in 2012 and found a third, temporary belt nobody had predicted. They also found that the quiet slot between the belts fills in with lower energy electrons during almost every geomagnetic storm, not once a decade during extreme events, which is what scientists had long assumed. Not slightly wrong, structurally wrong, which leads somewhere that sounds trivial and is not. If exposure inside a capsule varies fourfold by position, then where a crew member sits stops being a question of comfort or hierarchy. Seat assignment becomes a radiation safety decision. Where you stow the water, the food, the equipment lockers, that becomes shielding architecture. On a long enough flight, the arrangement of the furniture is a medical intervention. On April 6th, Orion swept around the far side of the moon at about 6,500 kilometers, 4,067 miles, and for roughly 40 minutes the moon stood between the crew and Earth, and no signal passed either way. They reached 406,771 kilometers from home, 252,756 miles, farther than any human being has ever traveled. On April 10th, at 7 minutes past 8 in the evening, they splashed down in the Pacific off San Diego and walked to the medical bay under their own power. 10 days. In and out, through the fence and back, before anything had time to accumulate. But the fence is not the destination. The fence is the edge of the property. Past it, Earth's magnetic field does not end abruptly. It thins smoothly until it stops meaning anything at all. And into that thinning, two entirely different kinds of radiation arrive. One announces itself with minutes of warning and can be waited out. The other cannot be shielded, cannot be predicted, and gets worse the harder you try to stop it. Earth's magnetic field does not stop the way a wall stops. It falls off with distance gradually, the way a streetlight's glow fades as you walk away from it. Bright, then dim, then technically present and practically useless. Somewhere out there the field is still measurable and no longer protective. You do not cross out of the shelter. You dissolve out of it. And into that dissolving, two entirely different kinds of radiation arrive. They come from different places. They behave nothing alike. And almost everything difficult about deep space flows from the fact that the defense against one of them makes the other one worse. The first kind begins on the surface of the sun. The sun's outer layers are not solid. They are plasma, a fluid of charged particles, and that fluid drags magnetic field lines around with it as it churns. Over days and weeks, those field lines get twisted, wound, knotted. Picture wringing a wet towel again and again in the same direction until the fabric bunches and buckles against itself. Eventually the knot slips. When it does, the stored magnetic energy releases in minutes, and a fraction of it goes into flinging protons outward at a substantial fraction of the speed of light. Scientists call the result a solar particle event. Here is the part that governs everything about how crews respond to one. On August 4th, 1972, astronomers watched a major flare erupt from a region on the Sun's face. Significant fluxes of high-energy protons began arriving at Earth's distance less than 40 minutes later. 40 minutes. Less time than it takes most people to eat lunch. That is the entire gap between seeing the flare and being inside the consequence. And for the fastest particles, the window is shorter still. That August storm has a particular place in the history of spaceflight because of when it happened. Apollo 16 had splashed down in April. Apollo 17 would not launch until December. The event fell almost exactly between them. What would have happened to a crew caught in it? Scientists have argued about this for 50 years, and the honest answer depends entirely on where the astronauts were standing. An astronaut on the lunar surface in a spacesuit, a suit designed for micrometeoroids and temperature, not for proton storms, would have been in serious danger. Multiple analyses conclude that a thinly shielded person on an extended moonwalk could have received a dose in the range where acute radiation sickness becomes likely, and some place it near the fatal threshold. Inside the command module, the picture is different and more contested. One NASA study, using biological models originally built for nuclear warfare casualty estimates, concluded that the risk of early death behind Apollo shielding was very small, particularly with prompt medical treatment. Other assessments agree that death inside the vehicle was unlikely, but that vomiting, fatigue, and damage to blood-forming organs would have been difficult to avoid. Both conclusions come from real measurements of the same event. The disagreement is not about the sun. The disagreement is about how human bodies respond at doses nobody has ever deliberately delivered to a person, and that gap has never closed. Ice core evidence suggests events considerably larger than 1972 have occurred in the past several centuries. The largest known appears to be the Carrington event of 1859, by some estimates roughly 4 times the size. So what does a modern crew actually do? Here is the thing most people picture wrongly. When you hear storm shelter, you imagine a reinforced compartment, a lead-lined room somewhere in the ship. That room does not exist, because every kilogram of dedicated shielding is a kilogram that must be lifted out of Earth's gravity at enormous cost. Orion's solution is stranger and much more human. A radiation detector inside the capsule sounds a warning. The crew then opens 2 large storage bays beneath their seats, pulls out the stowage bags, bags holding food, water, supplies, the ordinary freight of a voyage, and rebuilds them into a wall around themselves, packing the densest bags against the parts of the hull with the least protection. They have up to an hour to do it. In some scenarios, they stay inside for as long as 24 hours. Think about what that means. The shelter is made of dinner. The protection is the mass of things they were going to eat anyway, stacked into a fort. NASA engineers have rehearsed the procedure in mock-ups on the ground, timing how fast 4 people can build a wall out of their own supplies. And while it happens, there would be nothing to see. For a moment, place yourself inside that capsule during an event. You feel nothing. The particles pass through the hull, through the bags, through your body, without any sensation at all. No heat, no pressure, no sound. The lights do not flicker. Through the window, the sun looks exactly as it did an hour ago. The only evidence anywhere in the vehicle is a number on a dosimeter, climbing, then holding, then hours later, stopping. You would climb out of that fort, put the food back, and go on with the flight schedule. And the only thing that would have changed is a figure in a file at Johnson Space Center, the running total of every millisievert you have ever absorbed, which just moved permanently in a single afternoon and will never move back down. That is the first kind of radiation, sudden, survivable, and shieldable, if you are quick. The second kind cannot be waited out because it never stops. Galactic cosmic rays do not come from the sun. They come from outside the solar system entirely, accelerated, we believe, by the shock waves of supernovae, stars that exploded long before the Earth existed. They have been traveling for millions of years, and they are not protons. Or not only protons. The dangerous component is nuclei of heavy elements, oxygen, silicon, iron, stripped bare of their electrons and moving at close to light speed. An iron nucleus at that energy behaves nothing like the radiation you have encountered in a hospital. An X-ray is a photon that scatters. This is a dense, heavy, charged bullet that travels in a straight line, punching through hull, through insulation, through skin and muscle and bone, ionizing a narrow column of everything it touches along the way. Picture a needle pushed straight through a stack of paper. The hole goes through every sheet, in the same place, on one track. Now picture that track running through a cell, and the paper being the double helix inside it. Cells repair damage constantly. They are very good at fixing a broken strand. They are considerably less good at repairing a straight tunnel bored through a whole cluster of molecular machinery at once, and this rain never stops. Not for an hour, not for a day. Every second of the voyage, in every direction. The obvious answer is more shielding. Build thicker walls. Except this is where the physics turns against us, and it is the single most counterintuitive fact in the whole field. When a high-energy iron nucleus strikes an aluminium wall, it does not simply stop. It shatters. The collision breaks both the incoming nucleus and the target atoms into a spray of lighter fragments, protons, helium nuclei, and, critically, free neutrons. You have converted one bullet into a shotgun blast. Physicists call this fragmentation, and it cuts both ways. Breaking up heavy ions genuinely does lower the biological damage from that component, but the shower of secondaries it creates, particularly the neutrons, can raise the overall harm behind the shield. NASA's own modelling has shown cases where adding more aluminium beyond a certain thickness increases the dose rate at the point you are trying to protect. Add armour, get hurt more. There are few sentences in engineering more unwelcome than that, which is why the search has moved toward hydrogen-rich materials, polyethylene, and above all water, which fragments incoming nuclei far more cleanly and produces a less vicious secondary field. Water, of course, is also something the crew must carry anyway. Now, the relief. And even the relief comes with a bill attached. An active sun suppresses galactic cosmic rays. When the sun is at its most violent, it pushes a denser, more turbulent magnetic field out through the solar system, and that field deflects a substantial fraction of the incoming interstellar particles before they reach the inner planets. Solar Cycle 25, the current one, has been the strongest in about 2 decades, and has produced the deepest cosmic ray suppression in that span. So, the quiet sun is the dangerous sun for the constant rain. The angry sun is the dangerous sun for the sudden storm. Artemis II flew during the active phase of that cycle, the safer window for cosmic rays, the riskier window for a solar event. That is not a solved problem. That is a trade, made deliberately, with real stakes on both sides. We know what interplanetary space actually delivers, because a machine carried a detector through it. When the Mars Science Laboratory flew the Curiosity rover to Mars in 2011 and 2012, an instrument called RAD sat inside the shielded cruise stage, measuring, deliberately positioned to approximate what a crew would experience inside a similarly built spacecraft. The result? Published in Science by Carrie Zeitlin and colleagues at the Southwest Research Institute. An average galactic cosmic ray dose, equivalent of 1.8 millisieverts per day. Zeitlin gave the comparison himself, and nothing has improved on it. In terms of accumulated dose, that is roughly a full-body CT scan every 5 or 6 days. Every 5 or 6 days for the entire crossing, with no way to decline the scan. Total for the transit phases alone, out and back, with current propulsion, not counting a single day spent on Mars, approximately 0.66 sieverts. Hold that number, because of what it collides with next. Following a National Academies review in 2021, NASA moved toward a single career radiation limit for all astronauts regardless of age or sex, about 600 millisieverts, set at the level calculated for the most vulnerable case, a 35-year-old woman. The European Space Agency, the Canadian Space Agency and the Russian Agency use a career limit of about 1,000 millisieverts, 1 sievert. Set those beside the measurement, a Mars round trip, transit only, runs around 660 millisieverts, which means a crew flying under NASA's standard could exceed their entire career limit before they ever touch the surface, and would exceed it again on the way home. The same crew, flying under European or Russian standards, would be inside the line, though not by a comfortable margin. Add a 500-day surface stay, and estimates push the total to roughly 1 sievert or beyond. Nobody is hiding this. Both numbers are published. Both were set by serious committees using defensible models. They simply disagree about how much risk a person may consent to, and a limit is not a physical fact about the universe. A limit is a decision about acceptable harm, and different institutions have made different decisions. If NASA's limit holds as written, some astronauts could return from a first Mars mission and never be assigned to another flight. One voyage, and the career is complete, and underneath the cancer numbers sits a second question that worries mission planners considerably more. Researchers at the NASA Space Radiation Laboratory at Brookhaven fire beams of iron, silicon, oxygen, and titanium ions at rodents, then run them through cognitive tasks, object recognition, attention set shifting, the animal equivalents of noticing that something has changed and adjusting your approach. Across many laboratories, the results have been consistent and unwelcome. Measurable impairment at doses in the range a Mars crew would actually accumulate. One study using a facility built to deliver realistic low-dose rates over 6 months extrapolated that roughly 1 astronaut in 3 might experience difficulty with episodic memory. Here is the problem, and the researchers state it themselves. A rodent is not a person. A beam of one ion species is not the mixed field of deep space. An accelerator delivers in minutes what space delivers over a year, and biology is often exquisitely sensitive to that difference. Some analyses note that even after correcting for the greater damage heavy ions cause, the effective doses involved sit far below the thresholds where neurological damage is clinically detectable in humans, which is precisely why these findings forced a rethink of the underlying radiobiology rather than fitting neatly into it. So the field is split. One camp holds that the rodent evidence is strong, reproducible, and pointing at a genuine hazard to crew decision-making. Another holds that the extrapolation to human cognition is not currently supportable. Both camps agree on one thing: we cannot settle it without human data, and human data means sending people. Which brings us to what happens when a crew, carrying all of this, tries to ask Earth what to do. Light travels at just under 300,000 kilometers per second, about 186,000 miles per second. That is not a technology limit that better engineering will eventually beat. Nothing carrying information goes faster, ever. On the space station, the delay to the ground is around 1 1/3 milliseconds. To put that in your own body, a nerve signal takes roughly 20 milliseconds to travel from your fingertip to your brain. The station's signal reaches Earth more than 10 times faster than you become aware of touching something. Imperceptible does not begin to cover it. At the Moon, the delay is about 1 1/4 seconds each way, 2.5 seconds for a question and its answer. That is small, and it is not nothing. Listen to Apollo air-to-ground recordings, and you can hear the crews adapting. Longer sentences, more self-contained statements, fewer of the little interruptions and overlaps that fill ordinary conversation. 2.5 seconds is enough to make people talk differently. Not enough to stop them talking. Mars stops them talking. At closest approach, Earth and Mars are about 54.6 million kilometers apart, roughly 34 million miles. A signal crosses that in 3 minutes and 2 seconds. At their farthest, on opposite sides of the Sun, about 401 million kilometers, 249 million miles, 22 minutes and 18 seconds, one way, which makes a single question and its answer 44 minutes and 36 seconds. Ask something at the start of a lunch hour and the reply arrives as you are finishing. That is not a bad phone connection. That is a different kind of relationship. You stop conversing and begin exchanging correspondence, and everyone who has ever written letters across an ocean knows what that does. You start answering questions the other person has stopped caring about. They send reassurance about a problem you solved 2 hours ago. Every message you receive is a message from your own past, addressed to a version of you that no longer exists. Here is what makes this genuinely strange and worth being precise about. Contact is not what is lost. The Deep Space Network, 3 enormous antenna complexes spaced around the Earth in California, Spain and Australia, can detect signals from Voyager weaker than 1/1000,000,000th of a watt. We will hear a Mars crew perfectly well. What disappears is the illusion that Earth is with you now. Mission Control stops being a partner in the room and becomes a reader of your past, writing into your future. They cannot help you with what is happening. They can only comment later on what happened. NASA has begun training for this deliberately, on the ground. Inside the Human Exploration Research Analog at Johnson Space Center, crews spend 45 days in a sealed habitat with communication delays of up to 5 minutes each way, long enough that coordinating a simple task becomes an exercise in writing complete, unambiguous instructions the first time. The facility can impose delays of up to 23 minutes each way. In the Shapea habitat, a second crew of 4 completed a 378-day simulated Mars mission with 22-minute delays built in, and, at the midpoint, a deliberate 2-week total loss of signal. Not a delay. Silence. The point of these exercises is not endurance. The point is autonomy, specifically medical autonomy. Crews are being taught to diagnose, decide, and treat without asking, because asking will not work. Delay by itself is survivable. Humans have crossed oceans with letters that took months. People adapt to correspondence. But every one of those sailors was carrying something a Mars crew will not have. And the question that decides everything is not what happens when a crew is lonely, or bored, or out of touch. It is what happens when someone aboard needs help that cannot wait 44 minutes for a reply. Ask a flight surgeon what the most important piece of medical equipment aboard the International Space Station is, and the honest answer is not in the medical kit. The kit is good. It holds a defibrillator, an ultrasound, intubation gear, drugs, a surprisingly comprehensive set of tools for 4 to 7 people living in a metal cylinder. Crews train on all of it, but none of that is the asset. The asset is the capsule docked at the far end of the station, and the fact that from the moment a decision is made, a critically ill astronaut can be strapped in, undocked, deorbited, and lying on a steppe in Kazakhstan, with recovery helicopters inbound in roughly 3.5 hours. That is the number that makes station medicine possible, not the ultrasound. The exit. Every treatment protocol aboard that station is written as a bridge. Stabilize the patient, keep them alive, get them home. Space medicine in low Earth orbit is not really about curing anyone. It is about buying 3.5 hours. And that option does not degrade gracefully as you travel outward. It does not become 5 hours, then 12, then a day. It terminates. Completely. At a single, identifiable instant. The instant is the burn. When a spacecraft leaves Earth orbit, when the engine fires and the closed loop opens into an escape arc, the vehicle stops being somewhere you can come back from at will and becomes something following a path. Consider what that meant for 4 specific people in April of 2026. On flight day 4, the crew of Integrity were beyond 200,000 miles from home on a free return trajectory. Their path was designed so that the moon's gravity would swing them back toward Earth automatically. Elegant, efficient, and utterly committed. Suppose that on that morning, one of them had developed appendicitis. Not a dramatic emergency. The most ordinary surgical emergency there is, the one that sends about 1 in 20 people on Earth to an operating theatre at some point in their lives, and which is entirely routine to treat. There would have been no turning around. Turning around does not mean pointing the nose back at Earth. Space does not work that way. To reverse a trajectory that fast, that far out, you would need to cancel the entire velocity you have built up and then build it again in the opposite direction. A quantity of fuel no crewed vehicle has ever carried. The moon encounter was not a choice they could revisit. It was already, in a real sense, in the past. That appendix would have been handled inside the capsule, with what was aboard, by the people aboard. And here is the part worth being careful about. That is not a planning failure. Nobody forgot to include an escape option. The physics does not permit one. Translunar injection is a door that locks behind you, and everyone who has ever passed through it knew that when they strapped in. Which brings us to the most famous rescue in the history of exploration, and to the detail that almost every retelling leaves out. On April 11th, 1970, Apollo 13 launched for the Fra Mauro Highlands. 56 hours later, more than 320,000 kilometers from Earth, over 200,000 miles, Jack Swigert flipped a switch to stir the cryogenic tanks. Damaged wire insulation inside oxygen tank number 2 ignited. The tank ruptured. It blew a panel off the side of the service module and damaged the second tank alongside it. Within minutes, both were venting into space, and the fuel cells that turned that oxygen into electricity and drinking water were dying one by one. Jim Lovell reported a main bus B undervolt. Then he looked out of the window and saw gas streaming away from his own spacecraft. 2 of the 3 things needed to stay alive were leaving, visibly, and could not be recovered. Firing the big service module engine to turn the stack around was considered and rejected. Nobody knew what the explosion had done to it, and lighting a damaged engine that far out, with no second chance, was a risk flight director Gene Kranz's team would not take. So the plan became something nobody had ever practiced. Use the moon. They moved into Aquarius, the lunar module, a vehicle built to carry 2 men down to the surface and back up again over about 2 days. It now had to keep 3 men alive for roughly 4. Think about that ratio. Not a small overrun. 3 times the load it was designed for. The crew rationed themselves to about 6 ounces of water a day each, less than a small glass. Power was cut to almost nothing, and the cabin temperature fell below 4 degrees Celsius, about 40 Fahrenheit. Condensation formed on the walls. Nobody slept properly for the rest of the flight. Then engineers used the lunar module's descent engine, an engine designed to lower a lander gently onto the moon, to reshape the trajectory of the entire remaining stack, first onto a free return, then to speed it up. A landing engine, repurposed as an interplanetary steering system, firing with a crippled ship bolted to the front of it. And then there was the air. The command module and the lunar module both used lithium hydroxide canisters to scrub carbon dioxide out of the cabin. But the command module's canisters were square, and the lunar module's sockets were round, because they were built by different contractors for different jobs, and nobody had ever imagined needing to swap them. With 3 men breathing into a 2-man cabin, the carbon dioxide climbed toward levels that caused confusion first and death after. Engineers in Houston assembled every object they knew was aboard the spacecraft onto a table. Then they built an adapter out of it: plastic stowage bags, cardboard torn from the flight procedure manuals, duct tape, and a hose from a lunar spacesuit. They wrote instructions. They read those instructions up to the crew. The crew built it. The carbon dioxide came back down. On April 17th, all 3 men splashed down alive in the South Pacific. That story gets told as a triumph of ingenuity, and it was. But almost nobody notices the single condition that made it possible. The delay was about a second each way. Houston asked a question. The crew answered. Someone in mission control heard the answer, thought about it, and asked the next one. Engineers in a back room could watch a number move on a screen and tell the crew what it meant while it was still moving. Read the transcripts and you can hear it. A conversation. Interruptions, corrections, clarifications, people talking over each other and sorting it out. 2 groups of human beings, one on a planet, one in a freezing metal box 250,000 miles away, functioning as a single team in the same present moment for 4 days. That is the fact that reframes the whole event. Apollo 13 was not simply a rescue. Apollo 13 was the last rescuable deep space emergency in human history, and it was rescuable because the moon happens to sit at the exact distance where light still moves fast enough to let people think together. Every emergency beyond that distance happens differently. The ground learns of it after it has already developed. Their advice arrives after the situation has changed. They are not a team member anymore. They are an audience. Now stretch the same picture across a Mars mission, and the shape of the problem becomes plain. Under the conjunction class profile that NASA's own design reference architecture uses, the lowest energy, most practical option, the outbound transit runs roughly 180 to 210 days. Then the crew waits at Mars for about 500 days, not because there is more to do, but because Earth and Mars must swing back into alignment before a return is possible, then a similar transit home, around 900 days, end to end, 2.5 years. Guess at which point in those 900 days a rescue could reach them. There is no such point. Not one. On day 2, on day 400, on day 890, the answer is identical. No vehicle exists that could be launched, could catch them, could bring them back faster than their own trajectory already will. The window never opens, because the window was never built. Sailors crossing the Atlantic in the 16th century had no radio, and no rescue either. But they had something a Mars crew will not. They could turn around. Wind is symmetric. Orbital mechanics is not. So what do crews actually do with that? They do something that has no real equivalent in modern life, though sailors would recognize it instantly. They stop treating the spacecraft as transport and start treating it as the world. Not the thing carrying you to safety, the only safety there is. You trust the hull the way a crew on a wooden ship trusted their hull, because doubting it changes nothing and costs everything. Practically, it means the crew becomes the hospital. Mars crews are envisioned at 4 to 6 people. Planning assumes at least 1 and preferably 2 will be surgically capable, able to open an abdomen, find a problem and close it again. Not a doctor standing by for consultation, a person who will physically do it, which means that during a Mars mission, an appendectomy would be performed in the vehicle by a colleague. A broken bone would be reduced and set on Mars. A cracked tooth would be treated by someone who trained for it in a dental chair years earlier and has not touched a drill since. An allergic reaction that closes an airway would be managed all the way to intubation, with equipment chosen years in advance under brutal mass constraints by whoever is nearest. Here is where an honest account has to slow down, because the picture is better than the horror stories suggest, and worse than reassurance would like. The obvious fear about surgery and weightlessness is blood. Droplets floating free, obscuring the field, drifting into a caregiver's eyes and airway. Researchers have tested this on parabolic flights, and the results surprise them. In microgravity, surface tension dominates. Blood tends to form domes and cling to tissue rather than spraying into the cabin. Studies with restrained operators and containment systems have completed surgical tasks with outcomes broadly comparable to normal gravity, and suturing in reduced gravity turned out to be slower, but not meaningfully worse. A recent review in the British Journal of Surgery concluded that open and minimally invasive techniques are feasible in microgravity, provided both the operator and the patient are properly restrained. That is genuinely encouraging evidence, and it is all simulation. No surgical procedure has ever been performed on a human being in space, not once in more than 60 years. Every conclusion rests on mannequins, animal models, and 20-second bursts of weightlessness in a diving aircraft. Surgeons who have done the parabolic trials have said the hardest part would not be the technique. It would be operating on a person you have lived beside for 8 months, and the crew going through that hatch will not be a healthy Earth-normal patient. A cluster of changes called spaceflight-associated neuroocular syndrome shows up in roughly 70% of astronauts on long missions: swelling of the optic disc, flattening at the back of the eyeball, folds in the tissue behind the retina, a drift toward farsightedness. Some of it persists after landing. Fluid shifts toward the head in weightlessness are almost certainly involved. Beyond that, the cause remains unresolved, with competing hypotheses about intracranial pressure, drainage systems around the brain, even sleep. NASA classifies it as a red risk for Mars, its highest concern category, while openly stating the pathogenesis is not well understood. No permanent vision loss has occurred yet. Nobody knows what 900 days does because nobody has ever flown 900 days. Then there is the immune system. Across shuttle and station missions, more than half of astronauts have been found shedding one or more latent herpes viruses: Epstein-Barr, varicella zoster, cytomegalovirus, in saliva or urine. These are viruses most adults already carry, held silent for decades by immune surveillance. In flight, that surveillance loosens, and the frequency and viral load rise with mission duration rather than leveling off. Almost all of it has been asymptomatic. A handful of astronauts developed minor symptoms. One long-duration crew member developed a skin rash linked to reactivation. Countermeasures remain unproven, so the crew performing surgery on day 400 will be doing it with a mildly compromised immune system, possibly with slightly altered vision, in a vehicle with no sterile theatre and a fixed quantity of antibiotics. Which leads to the sentence that mission planners say, quietly and rarely in public: some emergencies simply will not be survivable. A major stroke, a bleed inside the skull, a fast-moving infection that outruns the drugs aboard, a cardiac event needing a catheterization lab. Conditions that a hospital ward on Earth handles routinely, where the patient walks out 3 days later and tells the story at dinner, become terminal in transit, not because the medicine is unknown, but because the equipment weighs too much and the ward is 200 million kilometers away. Everyone planning these missions already knows this. It is not a hidden failure, it is a written assumption, and it forces a decision that no space agency enjoys discussing. Mission rules must pre-decide when treatment stops, not during, before launch. Somebody must write down, in advance, the conditions under which a crew stops trying, because a crew of 4 cannot make that judgment alone at 3 in the morning about a friend, and a mission control 44 minutes away cannot make it either. Crew selection changes shape too. Flight hours and engineering degrees have always been the currency of astronaut selection. For a Mars crew, the ability to hold a scalpel steady over a colleague may weigh as heavily as the ability to fly. If someone does die out there, the sequence is worth sitting with. The crew will know first. They will know for minutes, then hours, before anyone on Earth does. And by the time the signal arrives, they will already have done whatever people do. Said something. Held a moment of silence. Chosen where the body goes, according to a procedure written years earlier by people who hoped never to need it. Then the message reaches Houston, and a room full of engineers learns about a death that, for the crew, is already history. That is the strangest inversion of all. Earth becomes a mourner arriving late to a funeral it was never invited to, and the crew becomes, for that hour, the only people in the universe who know what happened. They will carry each other through it, because there is no one else. And that, in the end, may be the truest thing about deep space. It strips away every institution a person can lean on and leaves only the other human beings in the room. Rescue was one lifeline. Now it is gone. But a crew that cannot be saved can still be supplied, or so we have always assumed. Every voyage in history was kept alive by things arriving from somewhere else. That assumption fails next, and it fails in a way that is much quieter and much harder to notice while it is happening. Every voyage humans have ever made was kept alive by things arriving from somewhere else. Caravans met at wells, ships took on water at islands, Antarctic bases wait out the winter and then hear an aircraft. Even the most isolated expedition in human history was, in the end, a story about a resupply that eventually came. Nobody says this out loud because nobody has ever had to. The assumption is so old it feels like physics. Now look at the space station again and notice what is actually holding it up. You have probably heard that the station recycles almost everything, that it runs a closed loop, air and water going round and round. Here is what most people misunderstand about that. No closed loop is truly closed. Water seeps past seals in quantities too small to measure daily and too large to ignore across a year. Filters saturate and stop filtering. Sensors drift, slowly reporting values that are slightly wrong in a consistent direction, so that the system optimizes itself toward a target that no longer exists. Sorbent material sheds dust. Membranes foul. The station's life support is not a closed circle. The The station's life support is a very slow leak, topped up on a schedule by cargo ships. And the numbers behind that are worth walking through carefully because they are quietly extraordinary. And they are the reason a Mars vehicle is a fundamentally different kind of object. Each crew member aboard the station needs roughly a gallon of water a day, about 4 litres, for drinking, food, and hygiene. Almost none of that is fresh. The urine processor assembly distills urine under vacuum. What comes out the other side is water and a concentrated residue called brine, which still holds usable water inside it. For years, that brine was simply waste. Overall recovery sat between 93 and 94%. Then NASA added a brine processor assembly, a system using heated dry air and specialized membranes to squeeze the last moisture out of the leftovers. In 2023, Jill Williamson, the water subsystems manager for the station's life support, confirmed the result. Total water recovery had reached 98%. That sounds like a solved problem. Consider what it actually means. Launch 100 pounds of water. Run it through the system. 98 pounds come back. Run it again, a little over 96. The loop does not hold steady. The loop slowly drains, and every drop that leaves it is gone permanently, unless something arrives from Earth carrying more. On the station, something always does. A Progress or a Dragon docks, and the tanks top up, and the drain resets. And here is the detail that shows how hard those last percentage points are. The urine processor alone was designed to recover about 85% of pre-treated urine, and even reaching that was difficult, because calcium leaching out of astronauts' bones in weightlessness precipitated inside the distillation assembly and clogged it. Engineers had to reformulate the chemical pretreatment to fix it. Recovery from urine collected in the Russian segment, which uses different pretreatment, still runs closer to 70%. The first 90% is engineering. The last few percent is a decade of specialists arguing about chemistry. Water is the good news. Carbon dioxide removal aboard the station runs through the carbon dioxide removal assembly, beds packed with zeolite, a mineral with a molecular structure full of tiny cavities that trap carbon dioxide out of passing air. Heat the bed, and it releases what it captured. 2 beds adsorb while 2 desorb, switching endlessly. The concept is elegant. The hardware has been a long-running problem. Sorbent dust escaped the packed beds. In weightlessness, nothing holds loose particles down, and worked its way downstream into the check valve, the selector valve, and the air-save pump, jamming them. Engineers installed inline filters as a temporary fix while the bed containment was redesigned. Heater sheets ran near their thermal limits on every cycle and delaminated. Temperature sensors failed from fatigue. Published assessments place the mean time to failure for critical components often in the range of 500 to 1500 hours. 500 hours is 3 weeks. Eventually, the system could not be maintained indefinitely at all. Not because it broke beyond repair, but because components became obsolete and the parts stopped existing on Earth. NASA developed a redesigned replacement, the 4-bed system, and launched it in 2023. Oxygen tells a similar story. The oxygen generation assembly splits water into hydrogen and oxygen using electricity across a proton exchange membrane, producing roughly 2.5 to 4 kilograms of oxygen a day, about 5.5 to 9 pounds. Weightless to breathe, but a real, measurable mass of matter manufactured out of water every single day without a break, or everyone aboard dies. That electrolysis stack degrades. It requires periodic refurbishment. Refurbishment means removing hardware, replacing internal components, and putting it back, with parts flown up from a factory. Nobody can do that in transit to Mars. Mission architecture studies put the closure requirement for a Mars-class voyage at above 95% as an absolute floor, with NASA treating 98% as the operational target and pushing toward higher still. The station has just reached that number, in the one system where it is easiest to reach after 15 years of iteration, with a laboratory on the ground running parallel tests, with replacement filters and beds and pumps arriving every few months, and with engineers able to say, "Send us the failed unit, and we will tear it down. Take all of that away, and keep only the requirement." Now imagine the system slipping. Suppose recovery drifts from 98 to 97, then 96, over the first year of a 900-day flight. Could you not just launch a resupply after them? You could launch it. Physics decides what happens next. A chase vehicle must depart later, follow a longer path, and catch a target already moving at interplanetary speed, arriving, in the best cases anyone has modelled, many months behind. It would reach a crew who had either solved the problem themselves or had already died of it. By the time help arrives, the question it was sent to answer has been settled either way, which brings us to a threshold that is easy to state and very hard to feel. Whatever launches with that vehicle is functionally everything that will ever exist. Not most of it, not the important parts, all of it. Every seal, every valve, every circuit board, every gram of spare zeolite, every roll of tape, every replacement bearing, every antibiotic tablet. The universe available to that crew is a fixed and finite list, written by procurement officers years before departure, and nothing will ever be added to it again. Radiation was removed. Real-time contact was removed. Rescue was removed. Now, replaceability itself disappears, the quiet background assumption of every human life, that broken things can be replaced. Look at anything within reach of you right now and ask where you would get another one. That question always has an answer. On a Mars vehicle, for the first time in human experience, it does not. That single change rewrites engineering from the ground up. A seal on Earth is a consumable. A seal on a Mars transit vehicle must hold for a decade of thermal cycling with no inspection and no replacement. A valve that will be actuated tens of thousands of times must still actuate on the last day, after years of launch vibration and micro-shifting. Electronics face the strangest requirement of all. They must absorb the accumulated cosmic ray dose of the entire voyage, plus every solar particle event that happens to occur along the way. Events nobody can schedule, whose number and severity are unknown at launch, and still function on the return leg. You cannot test that. You can only build in enough margin that you believe you have covered it, and then find out. We do have one working example of designing for a universe with no shops, and it launched in 1977. The Voyager probes were built by engineers who assumed correctly that nothing would ever be repaired. So they built with brutal simplicity, redundant paths for critical functions, and margins that looked wasteful at the time. In November 1980, Voyager 1 finished its Saturn encounter and fired a set of trajectory correction thrusters for the last time. Those thrusters then sat unused. The spacecraft kept its antenna pointed at Earth using a different set, attitude control thrusters, which over the following decades slowly degraded as residue built up in their fuel lines. In 2017, with the primary set failing, JPL engineers asked whether the thrusters last used at Saturn could take over. They fired, after 37 years dormant. Think about the object that made that possible. A set of engines nobody had touched since the year the world was watching Saturn's rings arrive on television for the first time. Left in place, plumbed, wired, and carried across the solar system for 4 decades by people who never expected to need them. It happened again. In May 2025, with a set of roll thrusters clogging, the team revived a different set that had been considered dead since 2004, realizing that a circuit disturbance had probably flipped a heater switch rather than destroying anything. Todd Barber, the mission's propulsion lead, called it another miracle save. But notice what every one of those saves actually depended on. Not brilliance in the moment, though there was plenty of that. Hardware. Physical, redundant, already installed hardware, bolted on by engineers in the 1970s who could not know what would be needed and built it anyway. Every spare not built in at launch is a spare that will never exist. There is no cleverness that manufactures a thruster you did not bring. Now, the part of this that plays out not as a crisis, but as a mood. Picture the routine on day 200 of a Mars transit. Once a week, someone reads out the recycling efficiency. It is a number on a screen, checked, logged and filed. Week 1, 98.1, Week 2, 98.1. Week 9, 98.0. Week 23, 97.9. None of those changes matters. Every one of them sits inside the noise. Nobody would call the ground about any single reading, and the ground could not answer usefully anyway. But someone aboard will eventually plot them, and somewhere around the middle of the voyage, a crew member with time on their hands will fit a line through 18 months of weekly readings, extend it forward to the return date, and see where the trend lands. That is the moment, not an explosion, not an alarm. A person at a laptop, looking at a straight line on a graph, doing arithmetic they cannot undo. Slow drift is invisible week to week and decisive across a decade. Anyone who has watched a roof stain spread or a parent age knows exactly how this feels. Nothing happens, nothing happens, nothing happens. And then you look at an old photograph. Sailors are the obvious comparison, and up to a point the comparison holds beautifully. Wooden ships crossed oceans carrying everything they would ever have, repairing themselves with what was aboard, sailors trusting a hull the way these crews will have to. Except every one of those ships was heading towards something. Land. Any land. An island with drinkable water and trees for spars and a beach to careen the hull on. The whole logic of maritime survival was that the world contained places, and places contained materials. Between Earth and Mars, the world contains nothing. No moon offers air, no asteroid offers warmth. Nothing in the Kuiper Belt has water you can drink, timber you can cut, or a workshop you can borrow. And even arriving somewhere does not help in the way instinct insists it should. Reaching Mars does not solve a life support problem. Reaching Mars introduces dust, a new thermal environment, a descent, and an ascent. A fresh set of ways to break the vehicle you are relying on. Landing is not a solution. Landing is another problem. And the supplies do not simply sit there waiting to be used. Some of them are quietly dying in the cupboard. In 2024, a team led by researchers at Duke published an analysis in NPJ microgravity of the entire 2023 station formulary, 106 medications, cross-checked against 4 international drug registries. Of the 91 for which shelf-life data existed, 54 had an estimated shelf life of 36 months or less. 14 would expire within 24 months. A Mars round trip runs roughly 24 to 36 months. So more than half the medicine cabinet expires before the crew gets home. The painkillers, the antibiotics, the allergy medication, the sleep aids. Daniel Buckland, the senior researcher, put the practical reality plainly. Expired drugs are not necessarily useless, but agencies will have to plan on them being less effective, exactly as you would treat the old bottle at the back of your own bathroom shelf. Then the story turns in a direction nobody expected. The obvious culprit is space itself, radiation degrading the chemistry. But when researchers looked closely, spaceflight was not the main problem. A comprehensive analysis of 6 flight stability studies covering 36 drug products found that after up to 2.4 years in orbit, potency stayed within about 10% of match controls on the ground, with roughly a 1.5-fold increase in degradation rate. Real, but modest. The factor doing the most damage appears to be the plastic bag. To save stowage volume, medications are removed from manufacturer packaging and repacked into resealable bags. Those bags let atmospheric moisture and oxygen permeate. Studies now point to that non-protective repackaging, not radiation, not weightlessness, as the strongest driver of premature drug failure. The most striking single result comes from NASA pharmaceutical work on augmentin, a common antibiotic combination. Under current repackaging practice, researchers found clavulanate, one of its 2 active ingredients, was almost entirely gone after 1 month. 1 month? On the ground, in the bag. In June 2026, Southwest Research Institute published its own evaluation of NASA's handling protocols and reached the same conclusion. active ingredients degrade measurably faster when stored in bags? The proposed answer is to manufacture drugs on board, synthesizing what is needed when it is needed. The concept is genuinely promising and genuinely unproven. NASA's own exploration medical strategy documents state that no validated framework yet exists for assessing the stability and safety of what such a system would produce. So the honest position is this: we know the cabinet will expire. We do not yet know how to stop it, and we do not yet know how to replace it, which is why spare parts thinking has shifted toward fabrication, printers, feedstock, and the ability to make a component that was never carried. Bring the capability rather than the object. It is the most promising idea in the field, and it is still, today, a promise. Step back and look at the shape of what has happened. The magnetic shelter, gone at the belts. The sense of Earth being present with you, gone to the speed of light. Rescue, gone at the burn. And now, resupply, and with it the whole idea that a broken thing can be replaced. 4 connections, none of them returns. Not one of them comes back at any distance further out. And every single thing described so far, the shielding, the antennas, the arrays, the electrolysis, the warmth in the cabin, has quietly assumed one condition that has held all the way from low orbit to Mars and beyond. Sunlight. Not sunlight as scenery. Sunlight as electrical power and as heat. Past Jupiter, that assumption fails too, and it fails not gradually, but according to a law so simple you could write it on a napkin, and so unforgiving that it has quietly decided which parts of the solar system humans can reach at all. Light does not run out. Light spreads. Picture a candle in a dark room. Step back one pace and it dims. Step back another and it dims again, but not by the same amount. The light leaving that flame is spilling outward across the surface of an ever-growing sphere, and the surface of a sphere grows with the square of its radius. So the light landing on any one patch falls with the square of your distance from the flame. Double the distance, and you get a quarter of the light. Not half, a quarter. Physicists call this the inverse square law, and you could write it on a napkin. It is also the single most consequential fact about the outer solar system. Take one solar panel, a real one, unchanged, the same silicon and gallium arsenide, and hold it in sunlight here at Earth. Say it delivers 1,000 watts, a kettle, a hairdryer at full blast. Real, usable power. Now carry that same panel outward and watch what happens. At Mars, 1.5 times further out, the panel gives about 430 watts. Still respectable, a desktop computer running comfortably. At Jupiter, roughly 5.2 times Earth's distance from the Sun, the same panel yields about 37 watts. You have gone from a kettle to a dim reading lamp. At Saturn, under 11 watts. A single household LED bulb. At Uranus, under 3 watts. Less than the trickle charging your phone overnight. And at Neptune, 30 times Earth's distance, that same panel, same hardware, same star, produces barely more than 1 watt. The indicator light on a television standby. Same sun, same panel, reduced across a single solar system from a kitchen appliance to a pilot light. That is not an engineering failure anyone can fix. That is geometry, which raises the obvious response: build a bigger panel. NASA tried, and the result tells you exactly where the practical ceiling lies. The Juno spacecraft, launched in 2011, became the first solar-powered mission ever to operate at Jupiter. To do it, engineers gave it 3 solar arrays, each roughly 9 meters long, about 30 feet, carrying 18,698 individual solar cells across some 60 square meters of collecting surface. NASA's own visualizations compare the spacecraft's span to a regulation basketball court. At Earth's distance, those arrays could generate around 14 kilowatts, enough to run a small house. At Jupiter, Juno operates on roughly 400 to 500 watts. Rick Nybakken, Juno's project manager at JPL, put the arithmetic plainly at the time. Jupiter sits 5 times further from the Sun than Earth, and the sunlight arriving there packs about 25 times less punch. And here is the detail that should stay with you. Roughly half of that hard-won electricity does not run a single instrument. Half of it goes to keeping the spacecraft warm. Juno holds the record. Every other mission that has gone further out has run on something else entirely. Beyond Jupiter, spacecraft carry their own sun. A radioisotope thermoelectric generator contains plutonium-238, an isotope that does nothing but decay, steadily, predictably, for decades. As it decays, it produces heat. That heat is applied across junctions of 2 different metals, and the temperature difference between the hot fuel and the cold of space drives an electric current. No combustion, no fuel line, no moving parts anywhere in the system. Nothing to seize, jam, wear out, or run dry. A standard heat source module holds about 600 grams of plutonium dioxide, roughly the weight of a can of soup, and produces around 250 watts of heat, continuously, for the rest of your life and most of your children's. The conversion is spectacularly inefficient. Thermoelectric generators turn only about 5 to 7% of that heat into electricity, which sounds like a design flaw. Out there, the waste heat is half the point, and we will come back to why. Voyager 1 launched in September 1977, with 3 of those generators producing about 470 watts. They lose roughly 4 watts every year. 4 watts. Less than a small LED bulb. On Earth, a rounding error. On Voyager, 4 watts is the difference between a sensor that operates and a sensor that does not, between a heater held in reserve and a component running colder than anyone tested it for. By recent reporting, the spacecraft is producing less than half its original output, something in the region of 220 watts, with the transmitter alone drawing around 23 of them. So NASA has been switching things off, one at a time, for decades. Voyager 1 launched with 10 scientific instruments. The first was shut down in 1980. The most recent came on April 17, 2026, when engineers at JPL sent commands to power off the low-energy charged particles experiment, an instrument that had been running almost without interruption since the spacecraft left Cape Canaveral in 1977. 48 years of continuous measurement ended by a command that took more than a day to arrive. By NASA's own status listings, only a couple of science instruments remained switched on. Suzanne Dodd, the Voyager project manager, has been blunt about the situation. Electrical power is running low, and without shutting instruments off, the mission would have only months left. And here is what makes it strange, rather than sad. Nothing has broken, no component failed, no collision, no fault, no error. The spacecraft is doing exactly what it was designed to do, in perfect health, and it will die anyway, because the fuel inside it is simply running out, on a schedule set by nuclear physics in 1977. That is a kind of ending most machines never get. Not failure, just the arithmetic of decay, arriving on time. Now, the thing about Jupiter that nobody expected when we first went there. We knew Earth had a magnetic field and belts of trapped particles inside it. Jupiter has the same architecture, scaled up in a way that borders on absurd. Jupiter's magnetic field is roughly 20,000 times as strong as Earth's, and the whole structure whips around with the planet's 10-hour day. That combination captures charged particles and accelerates them to enormous energies, creating radiation belts, orders of magnitude more punishing than anything around our own world. Numbers make this concrete. On the surface of Europa, the icy moon we most want to visit, the radiation environment delivers something like 5,400 millisieverts a day. An unshielded human standing there would receive a NASA astronaut's entire lifetime career limit in under 3 hours, and by the end of a single day, 9 times that lifetime allowance in a dose that is overwhelmingly fatal. Move inward to Io, and the figure rises to several times that. For a moment, imagine you could stand on Europa's ice inside some impossible protective shell. Above you hangs Jupiter, filling a quarter of the sky, banded and turning. The ice underfoot is around minus 160 degrees Celsius, minus 260 Fahrenheit, hard as granite. The sun is a bright point, no longer a disk you could shade with a coin, and pouring through all of it, invisible, silent, is a flux that would kill you before that Jupiter finished a single rotation. We know exactly how that environment treats machines, because one machine lived in it for 8 years. The Galileo orbiter arrived at Jupiter in 1995 and eventually absorbed far more radiation than it was ever designed to survive. What followed was not one dramatic failure, but a long accumulation of small, strange ones. The tape recorder, the device storing every image for later transmission, began misbehaving. Engineers concluded that radiation had likely damaged a light-emitting diode or an optical transistor inside the circuitry, controlling the recorder's motor. The computer reset itself repeatedly. During a close pass by the small inner moon, Amalthea in November 2002, at least 5 separate radiation events occurred, any one of which would individually have thrown the spacecraft into protective standby. Instruments drifted out of calibration. Detector sensitivity fell. Picture a stone wall being worn down by rain. No single drop matters. No single drop is even visible. But the wall is measurably lower after a decade, and nothing you can do reverses a single drop. That is what happened inside Galileo's transistors. Atom-scale damage, one particle at a time, accumulating in silicon that nobody could reach. Most of the fixes had to be implemented purely in software, because software was the only thing left that anyone could change. So how do you send anything into that and expect it to work? 2 answers, and modern missions use both. The first is time. Juno flies a polar orbit specifically designed to dive between Jupiter and the worst of its belts, minimizing the hours spent in the fiercest regions. The second is a box. Juno's electronics sit inside a titanium vault, mounted at the heart of the spacecraft, sheltering the components that cannot be allowed to degrade. Europa Clipper, launched in October 2024 toward a moon we badly want to understand, carries the same philosophy in a different metal. A vault with walls of aluminium-zinc alloy, just under a centimetre thick, about ½ an inch. Kendra Short of JPL called sealing it a major milestone. When it closed on October 7, 2023, everything that would ever be inside it was inside it. A safe, a bank vault, built to keep radiation out rather than thieves, which is exactly where the story turned uncomfortable. In May 2024, with the spacecraft already shipped to Kennedy Space Center, the Europa Clipper team was advised that transistors similar to theirs were failing at lower radiation doses than expected. Roughly 1,500 of those transistors are embedded in Clipper. NASA described the underlying phenomenon as one the industry had not been aware of, a newly identified gap in the standard qualification process for transistor wafer lots, and the vault had been sealed 7 months earlier. Opening it would mean disassembling the spacecraft, replacing parts, resealing, requalifying, almost certainly missing the launch window, with the next opportunities years away. NASA ran testing around the clock at multiple facilities for 4 months and concluded in September 2024 that the spacecraft could complete its mission without major modification. Engineers identified mitigations, including operating certain switches sparingly and exploiting a process called annealing, where warming a damaged transistor can partially heal the accumulated damage. Clipper launched on October 14, 2024. Here is the honest tension, and it does not resolve. NASA's testing was extensive, and its analysis was reviewed. And the mission flew carrying components known to be weaker than specified, sealed inside a container nobody can open, into the most punishing radiation environment we routinely visit. The verification will be the mission itself. There is no consensus solution behind this either. Shielding versus mass has no agreed optimum. Every kilogram of armor is a kilogram of instruments or propellant you did not bring, and beyond a certain thickness, the armor stops helping and starts contributing problems of its own. Engineers argue about where that line sits, and they argue with real data on both sides. For crewed missions, one idea keeps returning: walls of water. Water shields well, and unlike lead, it is something a crew needs anyway. Drink it, then let it protect you. Elegant in principle. Nobody has ever built or flown one at the scale a human vehicle would require, and now the part that catches people out, because it runs opposite to instinct. Near Earth, the great thermal problem is getting rid of heat. Sunlight pours in, electronics run hot, and every spacecraft in the inner system fights to dump warmth overboard through radiators. Cross Jupiter's orbit, and that reverses completely. Sunlight has thinned to almost nothing. Equilibrium temperatures out there fall far below minus 150 degrees Celsius, around minus 240 Fahrenheit, and keep falling with distance. The vacuum will not conduct heat away, but radiation will drain it steadily into a sky at nearly absolute zero. Everything on a spacecraft has a temperature below which it stops working. Propellant freezes in its lines. Lubricants stiffen into wax. Coolant loops thicken and stall. Batteries lose capacity. Solder joints contract and crack. This is where that inefficient nuclear generator reveals its second purpose. The 90-odd% of plutonium heat that never becomes electricity is not wasted at all. It is piped, strapped, and radiated into the spacecraft to keep the machinery liquid and flexible. Cassini carried the idea further, with 82 radioisotope heater units scattered through its structure. Each one holds a pellet of plutonium oxide about the size of a pencil eraser, producing a single watt of warmth forever, exactly where it is needed. On Voyager today, the whole tightrope walk is visible in the operations log, engineers switching off heaters to save watts, while carefully ensuring the fuel lines do not freeze. Machines can be nursed through this. Bodies cannot. A spacecraft's electronics might tolerate a range of 100 degrees. A human being needs a habitat held within a band only tens of degrees wide, and inside that band, a much narrower slice before performance, judgment, and health start to suffer. Too cold and you lose dexterity, then consciousness. Too warm, in a sealed volume with no convection to help, and you cook. Holding that band in interstellar-grade cold means burning power continuously, for years, with no pause. Not occasionally, not when convenient, every second of every day for the entire voyage, or the crew dies of temperature long before anything else gets to them. And every kilogram of that warmth had to be lifted out of Earth's gravity, the generator, the fuel, the plumbing, the insulation, the redundancy, with rocket equations demanding tens of kilograms of propellant for every kilogram delivered on a trajectory that far out. Which is why any crewed Jupiter mission is not really a spacecraft at all. It is a small bunker, armored, heated, self-warming, radiation-hardened, that must be transported roughly 780 million kilometers, about 480 million miles, and then kept functioning for years with everything it will ever have already inside it. Nobody has built such a thing. Nobody is close. So Jupiter is where the environment turns actively hostile, a place that hits back, that damages the machines we send in ways we can measure and name. Push further out, and something unexpected happens. The danger quiets. Past the giant planets, the fierce belts fall away, the magnetic violence thins, and the radiation environment becomes, per hour, almost gentle. Nothing is trying to destroy your spacecraft anymore, and that is precisely where the missions become impossible, because out there, past Saturn, past the last place we have ever parked a spacecraft, the thing that kills you is not an environment at all. It is duration, and the fact that beyond a certain distance there is nowhere in the entire universe left to arrive. Nothing out here is trying to kill you quickly. That is the first thing to understand about the region past Saturn, and it runs against every instinct the word deep space produces. The belts are behind you. The fierce magnetic violence around Jupiter is behind you. Measure the radiation environment hour by hour, and it is, by outer solar system standards, almost mild. The Voyager data confirmed this decades ago. Per unit of time, the outer solar system is not more savage than the space between Earth and Mars. Nothing new arrives to attack you, and that is precisely the problem. Because when nothing kills you quickly, the thing that kills you is time. And out here, time is the one resource that expands without limit. On October 15th, 1997, a Titan rocket lifted Cassini off a pad at Cape Canaveral. The spacecraft was the size of a school bus, and it was going to Saturn. It did not go to Saturn. No rocket then or now could throw that much mass directly to Saturn with enough speed left over to stop. So Cassini went to Venus. Twice. Then back past Earth. Then out to Jupiter. 4 gravity assists. 4 separate borrowings of momentum from a passing planet, each one bending and accelerating the trajectory a little further outward. The spacecraft reached Saturn orbit on July 1st, 2004, 6.7 years after launch. Think about what that span contains. A child born on the day Cassini left Earth was in school, reading, with a favourite teacher by the time it arrived. The engineers who designed the orbit insertion burn had been working on other projects for years, and that is the fast route. Cassini took the efficient path, using every trick orbital mechanics allows. Voyager 2 did something more extraordinary, and it took far longer. Launched in August 1977, on a once-in-a-lifetime planetary alignment, it reached Jupiter, then Saturn, then Uranus, and finally past Neptune in August 1989. 12 years from launch to the outermost planet. A newborn at liftoff would have been finishing primary school when the Neptune images came home. Now, attach human beings to those numbers. A crude equivalent of Voyager 2's route means a decade of continuous human health. No serious illness, no unrecoverable injury, no dental emergency that becomes an infection. It means a decade of psychological function inside a sealed volume. And it means a decade of hardware operating without a factory, without a spare that was not packed, without a technician who was not aboard. One way. Everything we know about long-duration human spaceflight comes from missions measured in months. The longest single stay anyone has ever completed is a little over a year. Stretch that by a factor of 10, remove every safety net one at a time, and you are asking a question nobody has data to answer. But that is not the hardest part. The hardest part is what happens to conversation. At Jupiter, depending on where the 2 planets sit in their orbits, a radio signal takes somewhere between about 33 and 54 minutes to cross in one direction. Send a question at breakfast, and the answer might land before lunch. At Saturn, roughly 70 to 90 minutes each way. You ask something in the morning, the reply comes back in the early afternoon. At Uranus, around 2.5 hours one way. A single exchange consumes most of a working day. At Neptune, close to 4 hours in each direction. Ask a question at 9 in the morning, and the answer arrives around 5 in the evening. If the ground answers instantly, which they will not, because they will need to think, consult, and agree, which means an 8-hour turnaround, minimum, for one answer. At that point, something breaks that has nothing to do with engineering. A conversation requires that both people exist in the same moment. Strip that away, and what remains is not a slow conversation. It is correspondence, and correspondence has a property people forget until they experience it. Both ends are writing to someone who no longer exists. The crew member who composed a message at Neptune 8 hours ago has since eaten, slept badly, argued with someone, solved 2 problems and acquired a new worry. The person who reads it on Earth is answering a version of them that has already been replaced. And by the time the reply lands, the mission controller who wrote it has gone home, had dinner, and become someone slightly different too. Every message is a letter to a stranger, written by a stranger. For a moment, place yourself inside that. Imagine it is the middle of the night aboard the vehicle, the crew's arbitrary night, marked only by dimmed lights, because there is no sunrise out here to disagree with. You cannot sleep. something is bothering you that you cannot name. On the space station, you would put on a headset and hear a voice, a real one, answering, interrupting, laughing in the wrong place, somebody who is with you now. Out here, you can compose a message, and then you can lie in the dark for 8 hours knowing that the earliest possible comfort is most of a day away, and that whatever comes back was written to a version of you who has already stopped needing it. Earth stops being a source of guidance. Earth becomes a source of history. Push out further, and the geography itself thins into something barely worth the name. Beyond Neptune lies the Kuiper Belt, beginning near 30 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers, 93 million miles. So the Kuiper Belt starts 30 times further out than we are and extends toward roughly 50. Within or near that span orbit Pluto, Makemake, and Eris, worlds of rock and ice, each with its own strange chemistry. None of them a destination in any useful sense. Only one spacecraft has ever been there and looked closely. New Horizons launched on January 19, 2006, the fastest launch speed ever recorded for a human-made object. 9 years, 5 months and 25 days later, on July 14, 2015, it reached Pluto, passing about 12,500 kilometers above the surface, 7,800 miles, at roughly 14 kilometers per second. It could not slow down. It could not orbit. The entire encounter with a world we had waited 85 years to see lasted a matter of hours, and the critical imaging window was under 30 minutes. Then it kept going. On the 1st of January, 2019, it flew past a small Kuiper Belt object called Arakoth, still the most distant world any spacecraft has ever examined at close range. Here is something about that region that almost everyone gets wrong. Sunlight at Pluto is roughly 1,000th of what falls on Earth at noon. Say that aloud and the mind supplies an image of blackness, a world in permanent night, lit only by stars. That image is wrong. Noon on Pluto looks roughly like Earth does at dusk, in the minutes just after the sun has gone below the horizon. NASA even built a tool letting people find the moment each evening when their own back garden matches the light level on Pluto. You could read a book by it. You could see colors, shadows, the shape of a hillside. It is not darkness. It is twilight, held permanently across an entire world. If you could stand there, inside something that kept you alive on ground at around minus 230 degrees Celsius, about minus 380 Fahrenheit, the sun would still be the brightest thing in the sky by an enormous margin. Not a disk, a point, a single fierce star among the others, casting your shadow across nitrogen ice. But every solar technology we possess is useless there. The light is enough for a human eye, which is a spectacularly sensitive instrument. It is nothing at all for a power system, and even for cameras, exposures stretch out to lengths that would be absurd anywhere closer in. Enough light to read by, not enough light to live on. The signal timing at Pluto is where the abstraction turns concrete. When New Horizons made its closest approach, the spacecraft was about 3 billion miles from Earth, roughly 4.8 billion kilometers. A radio signal took around 4.5 hours to make that crossing, one way. 9 hours for a round trip. So, on the morning of the flyby, the spacecraft deliberately stopped talking. Every antenna, every instrument, every scrap of power was committed to the encounter itself. Mission Control in Maryland, after 9 years of work, had to sit through 9 hours knowing nothing at all. Not whether the images were good, whether the spacecraft still existed. If New Horizons had struck a fragment of debris at 14 kilometers per second, the event would have been over instantly, and the people who built it would have carried on hoping for another 9 hours, entirely unaware, because the news of its death was still in transit. The signal came back on schedule, but hold that shape in mind, because it is the shape of everything out there, which brings us to a distinction worth being precise about. Closer in, rescue is impossible in practice. The vehicle cannot turn around, a chase mission arrives too late, the medicine is not aboard. Those are engineering facts, and engineering facts sometimes change. Out here, rescue becomes impossible in principle. The problem is no longer that help would take too long to arrive. The problem is that help cannot even be informed in time to be relevant. The information about the emergency is itself moving at the speed limit of the universe, and it is losing. Work the example. A crew at Neptune has a catastrophic failure at 9 in the morning, their time. The alarm data leaves the vehicle immediately and travels for 4 hours. At 1 in the afternoon, Earth time, a room full of specialists watches a telemetry stream showing a crisis that began 4 hours ago. They work the problem. Suppose they are brilliant and fast and have an answer in 90 minutes. That answer departs at 2:30 and travels for 4 more hours. It arrives just after 6:30 in the evening, 9.5 hours after the event began. By then, the crew has already lived through the whole thing. They have solved it, or they have not. Earth's advice arrives like a letter offering suggestions about a fire that burned out before dawn, which leaves Earth with exactly one remaining role. Not command, not support. To watch, to wait, and to read the final messages in the order they arrive. So what would end such a mission? Not an event, not a strike, a storm, or a burst of radiation. The Voyager measurements make that fairly clear, hour for hour, that environment is not the danger. What ends it is accumulation, a failure with no fix, because the part that would fix it was never carried. A margin that narrows a fraction each year until, somewhere in year 7, it crosses a line nobody was watching. A thing that would be a 20-minute repair on Earth becoming a permanent condition of life. Deep space does not attack. Deep space waits and lets arithmetic do the work. And the same is true of the people. A crew out there stops being a crew and becomes something closer to a tiny civilization. One with no immigration, no births, no exits, and no strangers. The same 4 to 6 faces, the same voices, with the same verbal habits, in the same volume of air, the same food from the same manufacturing run, the same hum of the same fans at the same pitch for years. We have run versions of this on the ground, and the findings are consistent enough to be uncomfortable. Mars 500 sealed 6 men into a facility at the Institute of Biomedical Problems in Moscow for 520 days, from June 2010 until November 4, 2011, with a 20-minute communication delay built in. Antarctic winter overstations do something similar every year for real, with genuine inescapability. No aircraft can reach them through the polar winter. Across that literature, certain patterns keep reappearing. Crews split into subgroups. Small irritations calcify into resentments that outlast their causes. People withdraw. Others perform a relentless, effortful cheerfulness that costs them something to maintain. Many researchers describe a dip in mood and cohesion around the 3rd quarter of a mission, the point where novelty has fully worn off and the end is still not close. A review by Lawrence Palinkas, covering 26 studies and more than 1,000 participants, found interpersonal tension peaking in that stretch. The effect is real but contested. Some studies find it clearly, others do not, and researchers continue to argue about how universal it is. What nobody disputes is the underlying driver. These are not disorders. These are what ordinary, carefully selected, psychologically robust people do when they cannot leave. And then there is the finding that should genuinely unsettle anyone planning these missions. Russian researchers analyzing Mars 500 noticed something they called detachment, a progressive psychological separation of the crew from mission control. The crew told the ground less about their needs and problems and made more decisions independently, according to their own knowledge and priorities. The serious isolation studies confirmed it, and the numbers are stark. In the first 10 days of the Sirius 19 confinement, researchers logged 320 audio conversations between crew and mission control, totaling 11 hours. In the last 10 days, with communication equally available, 34 conversations, totaling 1 hour and 17 minutes. The crew simply stopped calling home. Here is where the science divides and it does not resolve. One reading holds that this is healthy adaptation, exactly what you want. A crew that must operate autonomously for years should stop reflexively deferring to a ground team who cannot help them anyway. Detachment is the psyche correctly updating to its situation. The other reading is a command authority problem. If a crew has drifted into treating mission control as background noise, then on the day the ground genuinely knows something the crew does not, a trajectory error, a systems trend visible only in the aggregate data, will they listen? Both positions come from the same experimental record. Neither has been tested where it matters, and underneath all of it sits a gap that no analog can close. Every isolation study ever run, Mars 500, Sirius, the Antarctic stations, the undersea habitats, happened on Earth. The participants were confined, monitored, and psychologically stressed, and every single one of them knew, at every moment, that the planet was directly beneath their feet. Space psychologists call the missing condition the Earth out of view phenomenon, the experience of looking for your homeworld and finding it indistinguishable from any other point of light. No human being has ever experienced it. Not one. The furthest anyone has travelled, Earth still hung in the window as a visible, blue, obviously home object. Researchers have proposed building habitats specifically to simulate it. Until someone does, the honest answer to what it does to a person is that we do not know, and we will find out with people already too far away to bring back. The small things matter more than they should. Every book, every film, every album aboard that vehicle was loaded once before launch, and the library is finite. A crew will reach the last unread page and the last unwatched film somewhere in the middle of the second year, and after that, there is only rereading. And every standard remedy for psychological strain, the ones every institution on Earth relies on, simply does not exist out there. Counselling, in any real-time sense, gone with the light delay. Rotation to a different posting, impossible. Time off, there is no off. Bringing in a new person to change the group dynamic, unthinkable. A walk outside, alone, to cool down after an argument, the single most ordinary human coping mechanism there is, and it does not exist. You cannot leave the room, not for years, not once, and yet, this is worth saying plainly, people have done remarkable things under exactly these conditions. Antarctic crews winter over and come back. Mars 500 finished. Human beings are extraordinarily good at building meaning inside small worlds when they have to, and the crews who fly these missions will almost certainly be better at it than any of us watching. But every one of them will still be carrying one last thing without noticing. Something so fundamental that no explorer in history has ever been without it. Not Polynesian navigators, not polar expeditions, not the Apollo crews, not Voyager itself, not even the people we have just imagined at Neptune. It is not a supply. It is not a system. It cannot be packed or built or rationed. And it has a boundary, a real, measurable physical edge, which two of our machines have already crossed. The sun does not simply shine, the sun exhales. From its outer atmosphere, continuously in every direction at once, a stream of charged particles pours outward. Protons and electrons stripped from atoms and thrown into space at roughly 300 to 800 kilometers per second. In more familiar units, somewhere between about 670,000 and 1.8 million miles per hour. Scientists call it the solar wind, and the word wind is doing something useful, because that flow does everything a wind does. It buffets, it pushes, it carries the sun's magnetic field outward with it, dragged into an enormous rotating spiral as the sun turns beneath it. It presses on planetary magnetic fields and shapes them. It takes the loose gas around a comet and combs it into a tail that always points away from the sun, regardless of which direction the comet is travelling, which is why comet tails look wrong to people the first time they think about it. And it fills a volume. Push a stream of anything outward, into a medium that pushes back, and you inflate a bubble. The interstellar medium, the thin gas and plasma and magnetic field that fills the space between stars, pushes back. The solar wind pushes out. Somewhere far past the planets, the two pressures balance. That bubble is called the heliosphere. And here is the thing that reframes everything. Every voyage described so far, the station, the moon, Mars, Jupiter, Neptune, Pluto, all of it has taken place inside it, not near it, inside. We have never in our history sent a human being outside the atmosphere of our own star. Only 2 objects have ever left. Voyager 1 crossed the boundary on August 25, 2012, at about 122 astronomical units from the Sun, 122 times the Earth-Sun distance. Voyager 2 crossed a different part of the same boundary on November 5, 2018. And here is what strikes me most about that moment, because I think most people picture it wrongly. Nothing happened. No shockwave, no flare of light, no shudder through the spacecraft. The boundary, the heliopause, is not a wall. It is a turbulent, shifting layer where one plasma gradually gives way to another, and the crossing is less like breaking through a membrane and more like walking out of a warm room into cold night air, in the dark with your eyes closed. The instruments did not detect an event. They detected a new steady state. The way scientists confirmed it was almost absurdly quiet. The plasma wave instruments measured the density of electrons in the surrounding space. Inside the outer heliosphere, that density runs at roughly 0.002 of an electron per cubic centimeter. Beyond the heliopause, Voyager measured values around 40 to 55 thousandths, a jump of roughly 20 times. That is how humanity found out it had left. Not a bang, a number on a graph going up and staying up. Sit with what that number represents. For the first time since those spacecraft were bolted together in a clean room in the 1970s, they were surrounded by material that the sun had never touched. Not deflected, not heated, not modified. Interstellar plasma, seeded by supernovae that exploded before the solar system existed, drifting through the galaxy on its own business, entirely indifferent to our star. Everything Voyager had ever flown through, everything either Voyager had encountered for 35 years, had been solar wind, our star's own exhaled breath. Now, extend that backwards. Every human being who has ever lived has lived inside that single structure. Every empire, every language, every childhood, every war, every piece of music ever written. All of it happened inside one bubble blown by one star. And here is the part that is genuinely strange to think about. Every star you have ever seen you saw through the solar wind. Look up tonight, and every point of light in the sky is reaching you across an interstellar gulf, then crossing the heliopause, then traveling 100+ astronomical units through our star's atmosphere before it enters your eye. You have never once looked at the universe from outside. Nobody has. The solar wind is everywhere around you at this moment, and you have never felt it, and you never will. So what actually changes at that boundary? The sun does not vanish. Gravitationally, its influence extends far further. The Oort cloud, the vast shell of icy bodies still bound to it, lies enormously further out. What changes is jurisdiction. Inside the heliosphere, the sun sets the terms. Its wind determines the density, the magnetic field direction, the particle population, the local weather. Everything is its atmosphere. Outside, the sun is still by far the brightest thing in the sky, a fierce, unmistakable point of light, but it is no longer sovereign. The plasma around you obeys the galaxy, not your star. The magnetic field draped through that space was shaped by processes hundreds of light years away. Leaving the solar system, in the truest sense, does not mean escaping the sun's gravity. It means leaving the region where your star has special standing. And this is where the science turns genuinely unsettled, in a way that should probably be better known. We do not know what shape the heliosphere is. For almost 70 years, the standard picture was a comet, a rounded nose facing the direction of the sun's motion through the galaxy, and a long tail streaming out behind, extending perhaps thousands of astronomical units. That is the image in every textbook. Then, in 2015, Merav Ofer of Boston University and James Drake of the University of Maryland ran a model that included the shaping effect of the solar magnetic field and got something else entirely. Not a single tail, but two jet-like lobes, squashed into a shape they described as croissant-like. Ofer has been open about the reception. She has said she was getting attacked at every conference and that she stuck to her position anyway. Then the picture cracked open further. Data from Cassini, an instrument built to study particles trapped around Saturn, which also detected particles echoing back from the heliosphere's boundary, suggested something different again. Tom Crimigis, who led experiments on both Cassini and Voyager, described the finding: not a comet, not a croissant, but very nearly round and symmetrical. A beach ball. He also described the reaction, which is the most human line in the whole debate, that the community had assumed a comet tail for more than 55 years, and you do not accept that kind of change easily. Meanwhile, Vladislav Ismodenov and colleagues in Moscow run models that agree the solar magnetic field confines the plasma into jets, but conclude the tail nonetheless extends for thousands of astronomical units. The disagreement is live right now. Both groups use real physics and real data. The models differ in how they treat processes like magnetic reconnection and how they handle particles picked up by the solar wind, and those choices produce different bubbles. The reason nobody can simply settle it is almost poignant. The nearest edge of the heliosphere sits more than 16 billion kilometers away, over 10 billion miles. 2 spacecraft have measured it directly. 2 points. We are trying to determine the shape of the structure containing all of human history from 2 measurements taken at its edge. Imagine determining the shape of a house you have lived in your whole life by touching the wall in 2 places, in the dark. And that bubble is not static, because our star is moving. The Sun is currently passing through a wisp of gas called the local interstellar cloud. Based on current estimates, it will exit that cloud within the next several thousand years. Though the figure carries real uncertainty, and researchers disagree about the timing, what happens then is honestly unknown. The heliosphere's size depends on the pressure pushing in from outside. Change the external medium, and the bubble changes, possibly expanding, possibly contracting, altering how much galactic radiation reaches the planets inside. We do not know. Nobody does. It has not happened while anyone was watching, which is part of the case for a mission that does not yet exist. Researchers have proposed an interstellar probe, a spacecraft designed from the outset not to visit anything, but simply to leave, deliberately and fast, targeting hundreds of astronomical units and ideally reaching around 1,000. Not exploration in the old sense, reconnaissance of the boundary itself from outside. The one machine already doing that work is running out of time. As of this year, Voyager 1 sits at roughly 170 astronomical units from the Sun, about 25.5 billion kilometers, close to 16 billion miles. Its radio signal, moving at the fastest speed the universe permits, takes around 23 hours to reach us, and in November of 2026, it becomes the first object humanity has ever made to be a full light day from Earth. Say that plainly. A message sent today arrives tomorrow. A reply arrives the day after. That milestone took 49 years of continuous travel at 17 kilometers per second, over 60,000 kilometers an hour, roughly 38,000 miles per hour, never slowing, never stopping since 1977. And a light year is 365 times further than that. Suppose we wanted it back. Not a rescue, nobody's aboard, just a reversal. Turn it around and bring it home. Work the physics. Voyager 1 is moving outward at 17 kilometers per second. To come back, you would have to cancel every bit of that speed and then build the same speed again in the opposite direction. Roughly 34 kilometers per second of velocity change, applied to a spacecraft with no fuel, 25 billion kilometers away. No engine humanity has ever built could do it. Not close. The trajectory is not difficult to reverse. The trajectory is finished, and it is not aimed at anything. Proxima Centauri, the nearest star to the Sun, lies about 4.25 light-years away. At Voyager's speed, covering that distance would take somewhere around 75,000 years, longer than all of recorded history multiplied many times over. But Voyager is not going to Proxima Centauri. It is not going to any star. NASA's projection is that in roughly 40,000 years it will pass within about 1.6 light-years of a faint red dwarf called Gliese 445, and pass within 1.6 light-years means it will not go near it in any meaningful sense. There is no destination out there. That is not a failure of mission planning. That is what interstellar space actually is. Which brings us finally to the protection nobody notices they are carrying. Every explorer in human history has had it. The Polynesian navigators reading swell patterns across the Pacific, the Mediterranean sailors hugging coastlines they could name, Shackleton's crew on the ice, the Apollo astronauts watching Earth shrink in a window. None of them had guaranteed survival. Many of them died. What they had was something quieter and more fundamental. Home was reachable, not certain, not easy. Reachable, a real place, in a real direction that could in principle be returned to. That single belief is what allows a human being to endure a long voyage. It converts suffering into a period with an end. Every coping mechanism, every act of endurance, every private negotiation people make with themselves at 3 a.m, all of it rests on the arithmetic of eventual return. Past the heliopause, that arithmetic breaks. Not because home is far, because the physics of getting back no longer closes. The velocity cannot be reversed. The distance cannot be shortened by any agency that exists or is realistically proposed. The sun behind you is still visible, still beautiful, still the brightest thing in your sky. But it is a star, not a home. The Voyagers will not stop. Their generators are fading by about 4 watts a year, and NASA has been switching off instruments one at a time to buy more years. At some point in the next several, the last of it goes. The transmitter falls quiet. The signal that has arrived, faithfully, every single day since 1977, simply does not come. And then nothing changes at all. They keep moving. Same speed, same heading, dark and cold, carrying golden records with etched instructions and greetings in 55 languages, sounds of surf and thunder, and a mother speaking to her child, records that will remain physically intact and perfectly readable for millions of years, aboard machines that will never again be able to answer a question. That is the truest image of deep space I know. Not a monster, not a void. A working object, still in perfect order, still going exactly where it was sent, and permanently unable to reply. Look back along the whole route, and the pattern is clean enough to say in one breath. The atmosphere thinned to nothing. The magnetic shelter ended at the belts. Real-time contact dissolved into correspondence. The lifeboat stopped existing at the burn. Sunlight failed as a source of power and of warmth. Resupply became impossible, and with it, replaceability. Then the destinations ran out, and finally, past the heliopause, the solar wind itself, the last thing our star was still doing for anyone inside it. 8 connections, each one left behind quietly, without ceremony, usually without anyone aboard noticing the moment it happened, and not one of them ever returns. Not at any distance. Not for any reason. The direction of travel is the direction of subtraction. So here, at the end, is the thing worth being precise about, because I think it is the whole answer. The universe never became crueler. The vacuum at 400 kilometers is the same vacuum as at 170 astronomical units. Gravity works identically everywhere. The speed of light has not shifted by a fraction. Cosmic rays out past the heliopause are not angrier than the ones that pass through your body while you sleep. Nothing out there escalated. Nothing was ever aiming at anyone. What changed at every threshold was how much of Earth was still doing the work. That is the entire story. Every protection we counted was not a property of space at all. It was a service being quietly provided by one planet, its molten core, its air, its relay satellites, its factories, its hospitals, its ability to send another one. Space is not terrifying because it is empty. Emptiness is peaceful. It is not terrifying because it is vast or cold or hostile. Those are just facts, and facts do not frighten anyone. Space is terrifying because it removes, patiently and without malice, every relationship between a traveller and the world that made them, one at a time, in order, never quickly enough to notice. Picture the view from out there, not from a spacecraft, from wherever you are tonight, imagining it. The sun is still the brightest star in that sky. It has no disk. It casts no warmth you could feel on your skin. It is a hard, white point among 10,000 others, distinguishable only because you know which one to look for. Beautiful, in the way any bright star is beautiful, and smaller than any human eye has ever seen it. Somewhere in the glare beside it, far too faint to separate, is a small blue world where every person you have ever loved is currently doing something ordinary. And there is nothing, no engine, no agency, no discovery waiting in any laboratory, capable of shortening that distance again. Which is why the most extraordinary fact in this entire story is not out there at all. It is that the one place in the known universe where none of these removals apply, where the air simply arrives and the ground holds you, and help is always in principle reachable, is the place you are sitting in right now. Not a shelter we built, a home that was already here. We have spent this whole journey discovering how much it was doing for us by watching what happens when it stops. Everything we followed tonight came down to a single sentence that nobody out there gets to say. If something goes wrong, someone will come. Apollo 13 had it. 4 days, a freezing lunar module, and a room full of people in Houston living in the same second as the crew, arguing, correcting, building a scrubber out of tape and cardboard. They came home because home could still reach them. Every voyage after that one gives it up, not because we were careless, because the universe simply stops permitting it past a certain distance. You still have it. Right now, wherever you are, there is a number in your phone that would answer. Someone who would get in a car at 2 a.m. without asking why. You have probably never counted that as an asset. Nobody does. It sits in the same category as the air and the ground and the molten iron turning under your feet. Things that were already running when you arrived, that nobody delivered, that you never once had to negotiate for. Space is not frightening because it is vast. It is frightening because it takes those things away, one at a time, so gently you would not notice. You are still inside all of it, still reachable. Thank you for staying with me this far. It was a long way out and a long way back. If it meant something, a like and a subscribe is how I know to keep making them. Sleep well. Someone would come.